all of Unit 3 falls under what we call function analysis. We are going to be able to, without the use of a calculator, understand, that's not how you spell understand, understand a function, its shape, what it looks like, its graph, interesting points on the function, through an analysis of its derivatives, an analysis of its tangent slope generators. I don't understand F by understanding F prime, by analyzing. So like think about what we did last unit. Last unit we spent the entire unit first introducing the concept of a tangent slope generating function. Brilliant, brilliant discovery that there is a function where you plug in x's and you get instantaneous rates of change of another function. Unbelievable. Brilliant. Okay? And we did some things with f primes. We found tangent lines. We found when certain functions had specific tangent slopes or specific rates of change. Great. But most of the unit was just understanding that if I give you an f, you should be able to give me its f prime. We learned a lot of rules of like, here's f, what is its f prime? Okay? Now, this unit, it is what are we going to do with it? What can we do with it? Okay? And what we can do and what we're going to get to in the end of this unit is I'm going to give you some like complex functions. X cubed minus 3x squared plus 3, x to the fifth plus 5x to the fourth. And through analysis of derivatives and tangent slope generators, you'll be able to accurately sketch these functions without using a calculator and without spending a lot of time just plugging in x's and getting y's. Okay? Any type of function. And you will need to have all of your derivative rules known because we have to be able to find the f prime functions easily to analyze them. Okay? The first thing we're going to talk about and analyze on a function are interesting points. Okay? In particular, interesting points like this point right there. Why is that an interesting point? Well, I'm going to call that point a max. It's like a local max. It might be the global max. Who cares? I don't care if it's like overall the max or locally a max. We'll just say it's a max. Okay? This point, that's a min. That's an interesting point on a function. Understanding where we got to go up, then go back down, or down, then back up. This point, max. Is it the overall max? No. It's a local max, but it's a very interesting point. This one right there. Interesting point on a function. Again, this is f of x. This is a function. These are interesting points on my function. It's a max. Cool. What do most of these points share in terms of some calculus things we've talked about? Discuss that with your neighbors. What do most of these points share? Very good. I heard it right away. The tangent slopes at all these points, except for this point here, is 0. This point here, what is the tangent slope? Yes, it's undefined. It's a sharp point. There is no tangent slope. Okay? Well, we are going to call these points critical points, but we'll call them something else as well. And a critical point is when f prime equals 0 or is undefined. And this is where we'll have max and mins. Max, min, locations of f. Now, question to you. If I have a tangent slope equal to 0 or a tangent slope that is undefined, am I guaranteed to have a max or a min? Discuss that with your neighbors. Are there situations where I could have a tangent slope equal to 0 but not have a max or a min? Turns out there is a location on the graph of f where I don't have a max or a min, but I have a tangent slope equal to 0. If we look a little carefully, it might not be obvious. Right here, if we look right here, my tangent slope is 0. However, at this location, I do not call that a max or a min because I go up, I flatten out, but then I keep going up. So I say it's not a max or a min. So we are familiar with this type of graph, a graph that looks like this. Just a quick example is like x cubed. X cubed has a tangent slope of 0 at 0. It kind of flattens out, then goes back up. I know it has a tangent slope of 0 at 0 because its tangent slope generator is 3x squared. And if I plugged in 0, I would get 0. But x cubed does not have a max at 0. It does not have a min at 0. Okay? So, turns out, whenever our derivative is 0 or is undefined, we will have possible max mins on f. Let me just write the examples of not a max or a min. When here f prime equals 0, right there, that's not a max or a min. So people are talking about a flat line, horizontal line. That was nice. I didn't really hear that in any other sections. Didn't even think about that. All the tangent slopes are 0, but it's not really a max where you go to the top and then come down or vice versa. If our f prime is undefined, there's two situations. One is a discontinuity. Like I do not have a tangent slope at this vertical asymptote, but my derivative is undefined. So it's not a max or min, obviously, at my vertical asymptote. I don't even have a point. So that's one situation. Another situation, which we haven't really talked about, but we're going to talk about now, and we're going to see with some of the functions that we analyze, when we have a tangent slope that is undefined because our tangent is vertical. What is the slope of a vertical line? It's undefined. It has a rise, it has no run. So vertical tangents, though you can see them, though you can sketch them, vertical tangents do not have a defined tangent slope value. Okay? So these are situations where at critical points, we do not have a max or min. Today, we're just going to be focused on finding these possible max-min locations. Okay? Next class, we will then be able to do the analysis to discover whether or not these possible max-mins are in fact maxes or mins. And we'll be able to see what type they are, whether they are a max or a min. Okay? So that's next class. It's figuring out if they are in fact maxes or mins. This class, we're just going to say, hey, here are locations on our function. They're interesting locations. They're going to be possible max min locations. Cool? Cool. Now, instead of saying max mins all the time, mathematicians use the fancy word extrema. Extrema. Long E. Extrema. There are two types of extrema that we will hear about. We're not going to really focus much on the difference. We'll kind of stick to one side of things. If we talk about like a global and overall max min, that's called an absolute extrema. If we talk about a local max min, which will include all of the global max mins, which is what we will focus on, this is called a relative extrema. In this unit, we will focus on relative extrema. They may so happen to be a global extrema, but we won't really care much. The absolute extrema, we'll talk about in a future unit. Okay, so for the first half of this lesson, you will be asked to find the critical numbers or the critical points or the possible extrema locations. Possible max-min locations. If I ask you to find the critical points, or find the critical numbers, or find the possible extrema, what do you do? Discuss with your neighbors. Right. It's like the question I asked you last unit, where does a function have a horizontal tangent? We are just going to find when does the tangent slope generator for all of my functions generate a slope of 0, or when is it undefined? Good. So we kind of understand. Something we've already done, but now we're going to see like why are we doing it? Because they're very possibly interesting points on our function. And we want to kind of understand our functions better using calculus. So all you need to do, using your knowledge of derivative rules, is find the tangent slope generator, set it equal to 0, but also don't neglect to see when it's undefined. Now, when do I have something that's undefined? When do I have an undefined function value? Yes, Mr. Corey, when I have a denominator equal to 0. Do I have a denominator for f prime? No. So I don't want to neglect it, but I can actually ignore it for this situation. And actually for the first 4 functions that we will look at, we do not have a denominator when I find the tangent slope generator. So I can ignore this undefined part. The last 2, we will. Well, now we just have to work on our factoring skills. Since I factor out the greatest common factor, which is an x, since x is factored out, 0 is a solution as well as 1. For right now, all we know is that these are possible max-min locations. It's pretty cool. We'll do more analysis next class. All right, next one. Pretty simple. Find the tangent slope generator. See when it generates a tangent slope of 0, or when it's undefined but doesn't have a denominator, don't have to worry about it. In this situation, I factor out a greatest common factor of 3. Since I factor out only a 3, 0 is not a solution. I hope we understand that. It's a mistake made with students is that they assume that if they factor out anything, 0 is a solution. But no, it's only if I factor out an x that I will have a solution of 0. Here, just -2 and 4 are possible maximum locations on F. Okay, not bad. Do the next two. And then we'll talk about these fractional powers. You know, two ways to handle the 3x squared minus 12. You can either factor, like we've been doing, and then we can factor the difference of squares, or you could solve this because you have an isolated x squared, but don't forget the plus or minus. Okay, so whichever way you chose, great. Okay, let's up the level of difficulty, try to write small. Here we go. Taking the derivative, I get 1/3 x to the, subtract 3/3 from 1/3. Don't tell me it's -1/3 because it's -2/3. Minus 4/3. See when that equals 0 or is undefined. In all of your previous examples, you did not have a denominator where x was in a denominator. Now I do. Let's catch up here. So I rewrite just so it looks a little bit nicer. Now, if I wanted to, I could combine these fractions, but I can't combine them to be like 1 minus 4 equals 3x to the 2/3 over 3. If I wanted to, I could give it a common denominator by multiplying the top and bottom of this by x to the 2/3. But like, I don't have to. And actually, I don't do it personally. I don't think it's necessary. Instead, I think if I ever have a denominator equal to 0, no matter if I have 1/0 plus anything or just 1/0, if I have a 1/0 somewhere or a number over 0 somewhere, it's undefined, okay? I have x in the denominator here. That means when 3x to the 2/3 equals 0, I will have an undefined derivative. When x is 0, I have an undefined derivative. This, my friends, is our first critical point, and this is what we need to keep in mind when I say when is our derivative undefined, when we have a denominator equal to 0. Possible maximum location, turns out it won't be. It'll be a location of a vertical tangent, but it's an interesting location nonetheless. But we don't know that yet. We're just going to start there. Now, the other solution or solutions will come from solving this. Okay. Since I just have one x, I can just isolate the x. So I can add the 4/3. I can flip both sides. You can cross multiply if you are so inclined to do so. You can divide by 3 just to get x to the 2/3 by itself. If I have x to any power, whether it's a fraction, a whole number, whatever it may be, and it's set equal to a number, though you haven't thought you've been doing this in the past, you have. You could take both sides to the reciprocal power. Because p to the 1 over p, if you take a power to a power, you get 1. And you've solved for x. You get x by itself. So, though you haven't thought you were doing it, when you were asked to solve x squared equals a number, you just say, oh, take the square root. You've been taking both sides to the 1/2 power. If you had x cubed, you say, oh, cube root. Well, it's the same as taking both sides to the 1/3 power. Now, you don't have to worry about this kind of technique with those because it's easy enough to just say, oh, just square root, just cube root. But if I have something to a fractional power like 2/3, I could take both sides to the 3/2 quickly, easily, one step, without roots, without two things going on. And what I would do to solve for x is take 8x to the 3/2 power. Because 2/3 times 3/2 is 1. We have solved for x. Now, question becomes, what is 1/4 to the 3/2? We know that we can write 3/2 as 1/2 cubed. The square root of 1/4 is 1/2. 1/2 cubed is 1/8. There's my answer. But, hold on a second. When I square rooted like right here, I got a plus or minus. Do I need a plus or minus here? You guys figure it out. Yes or no? Discuss. Let me see. If I plugged in -1/8 right there, and I take -1/8 to the 2/3 and I multiply it by 3, do I get 3/4? Well, let's see. I know -8 to the 2/3 is the same as -1/8 cube rooted squared. The cubed root retains its sign. This is -1/2. -1/2 squared is 1/4. 1/4 times 3 is 3/4. Yep. I need the plus or minus. I know. Sometimes I ask questions in certain ways, and you're like, oh, I think he's gonna be no or yes. In this case, it was a yes. We actually do need it. The reason why is like the square root of the square. This is x squared rooted, cube rooted. So because of the x squared, it'll make everything positive, which means I could have a negative value because when a negative value is squared, it becomes a positive. It's all about odds and evens, and in the numerator of your power, I don't want you to try to memorize a rule. Instead, just know that you need to go back and kind of check to see if you need positives or negatives. So this one's a tricky one. We needed negative 1/8, 0, and positive 1/8 are possible max and mins. Okay? The other one is not as tough. But it is a situation where we do need to consider when our denominator, any denominator, equals 0. The other solution will come from solving this. I added 1 to both sides. I flipped both sides. Did 3x to the 1/3 over 2 equals 1, or x to the 1/3 equals 2/3. How do you get rid of the 1/3? Cube both sides. 1/3 times 3 is 1. That's how we get x by itself. 2/3 cubed. If I have anything, a product, a quotient to a power, you would square, cube, whatever power of everything in this fraction. So 2 cubed, 8. 3 cubed, 27. Since I'm just cubing things, since this is the cubed root of x, the sign is retained. So if it was negative, it'd stay negative when I cube root it. When it's positive, it stays positive. So that's why I don't need a plus or minus in this situation. Because negative 8 over 27 cube rooted would give me negative 2/3. I don't want that. Trig functions have maxes and mins too. Let's find the locations of the maxes and the mins of these trig functions. We got sine pi x over 4. We got sine minus cosine. For this one, we got the chain rule. We don't have many derivative rules for these examples, but on your homework, you'll have like a chain rule. You'll have like a quotient rule. So let's not forget all of those rules. Don't forget the chain rule. We are back to a situation where we do not have a denominator, so we don't have to worry about the undefined part. We actually don't even have to worry about the pi over 4 that's outside. I could divide everything by pi over 4. And just like in the previous situations, I like to factor out just so I don't have anything disappear on me. But like I could have divided everything by 3, and this could have just disappeared on me. I don't like students to do that because sometimes like x's will disappear on them. We don't want that to happen because you're eliminating some possible solutions. So I instead just like to keep things factored, or in this situation, just don't worry about it. May go to lunch. I'm actually going to continue the lesson. That way it's just a continuous thing, and I'm not going to come back to it. So if you come back to class, you can watch the video. That'll be posted by the end of this class period. You do not come back here. You go straight to the college fair after lunch, okay? Homework is on the back on your way out. So I just kind of leave it because I don't like to get rid of stuff. But we know that whenever this equals 0, everything will equal 0. So let's solve this. Now, how do I solve this? I told you can either like forget about what's inside and just kind of solve for what's inside, or replace it with a different variable. So when is cosine equal to 0? That's at pi over 2 and 3 pi over 2 and all of the other vertical extremes. We should know this. We then set that equal to pi x over 4 to solve for x. So multiply by 4, divide by pi everything. The pi's will cancel. 4 divided by 2, that's 2. Here, 12 divided by 2, that's 6. We'll have more values associated with that. I'm not giving you an interval. I typically will give you an interval. Next one, derivative. Set that equal to 0 or undefined. Again, we don't have to worry about a denominator here, so I don't have to worry about when it's undefined. It's just when cosine and sine are opposites in the same values. Now, there are multiple ways to get to your answers, 3 pi over 4 and 7 pi over 4. You may just like look at this and say, oh, okay, this needs to be the opposite of this, same value, so you get them added together to get 0. Another way to handle this is if you like turn it into a tangent. So subtract cosine, divide by cosine. You get tangent x equals -1. And that's another way to get 3 pi over 4 and 7 pi over 4 and all the multiples of pi of those. Whatever works. Okay, but those are two examples of some trig functions and their critical points. Moving on. The second half of this lesson is about the mean value theorem. The mean value theorem is like the second theorem of the entire class that we have to know. Now, before we talk about the mean value theorem, we should talk and remember the intermediate value theorem, IVT, intermediate value theorem. And the IVT versus this is the MVT. Now, they're both going to start the same way. IVT started with 2 points. MVT is going to start with 2 points. So that's nice. Now, let's remember the intermediate value theorem. It said that if your function is continuous, and this is what was necessary, your function had to be continuous, then you're going to cross through all of the y values. At some location, at some x value, there's going to be a point where for some x in between these two x values, you're going to produce that y. So if I say, pick a y, connect your 2 points, you're guaranteed to have a x coordinate that produces that y coordinate. Boom. We have that in the interval. Now, since we are continuous, we did not have to connect in that way. I could have connected where we have a sharp point. And here now my solution would be right here, but it's still continuous even though we have sharp points. So the sharp point didn't change the intermediate value theorem. Mean value theorem deals with functions that are differentiable. Now we know the conditions for being differentiable. Conditions for being differentiable are you are continuous, but not only are you continuous, you do not have a sharp point. Okay? Well, if you're at home, go ahead and do this exercise for me. Connect your 2 points whatever way you want to, provided that we have a function, so we can't like cross over itself. We can't go like this. Okay, that's not a function. Provided we have a function and we connect these 2 points in a smooth, non-sharp point way. Let's go ahead and connect those 2 points in any way. Don't be afraid. I'm going to do this. Yeah, sure. What the mean value theorem states, I'm not going to write the whole thing out. I'm just going to say, you are guaranteed on your interval to have a location where the instantaneous rate of change of your function is equal to the average rate of change of your function. Now we know instantaneous rate of change is another word for tangent slope. We know that there will be a tangent slope somewhere that equals the average rate of change being the secant slope. There's some location on your interval where your tangent slope will equal your secant slope. Watch. No matter how you connect it, you got your 2 points, they create a secant line, and the slope of this line is the secant, the average rate of change. Okay? There is some location guaranteed by the mean value theorem where the slope of our tangent will equal the slope of the secant. Now, since we're talking about slopes and slopes being equal to each other, we know that we will create lines that are parallel to each other. So here, right around here, I have a location where my tangent slope equals the secant slope, which means these 2 lines are parallel with each other. The mean value theorem guarantees that there is at least one x location for this to occur. Now, you might not have connected your points like that. You might have connected your points in another way. Let's say you did that. Well, and then in your case, you have not only 1, but 2 locations. That's great. Mean value theorem guarantees there's at least 1. Okay? And that's it. To show that you understand the mean value theorem, I can give you some graphs and say, hey, here's an interval. Show me your understanding of the mean value theorem. Show me the approximate locations of f of x guaranteed by the mean value theorem. Well, here I gave you the 2 points that are on your interval. So I was being nice to you. You can visualize the secant slope. And then you're thinking, oh, when is my tangent slope equal to, or when will I have parallel tangent lines to that secant line? Approximate those locations. If you are able to sketch this, you know what you're doing. For this interval, I did not give you points, which means you need to produce the points on your function. So from -2 to 2, these are x's. So from -2 to 2, here, this slope would be the average rate of change of my function, on average how quickly the function's going up. And it looks like around here, my instantaneous rate of change is equal to my average rate of change. This is showing me I understand the mean value theorem. Now, we have another theorem called Rolle's theorem. It is an extension of the mean value theorem. It just has to deal with your 2 points having the same y. So say I got a point here and a point here. Same thing as the mean value theorem. Average rate of change and instantaneous rate of change equal each other. Only I know that the average rate of change for any 2 points, no matter where they are, if their y values are the same, the secant slope will always be 0. So we can be a little bit more specific in this situation. Okay? So no matter how I connect these 2 points, as long as it's smooth, no sharp points, I'm guaranteed to have tangent slope giving me that same slope of that secant. Okay? Here we go, let's do some problems. This first one, we'll find ends up following Rolle's theorem. So I want to show that the function follows the mean value theorem on the interval. So I'm thinking, when do my tangent slopes equal my secant slope? I need to find my secant slope, and the only way to find my secant slope is to get some points. If I plug in 2, I get 16 minus 8, which is 8. If I plug in negative 2, I get 16 minus 8, which is 8. So my slope of my secant, using the slope formula, 8 minus 8 over 2 minus negative 2, 0 over 4, it's 0. So this is a situation where we have like Rolle's theorem. We are guaranteed to have a tangent slope somewhere in between negative 2 and 2 that equals my secant slope of 0. My tangent slope generator, f prime, 4x cubed minus 4x, equals 0. Factor out of 4x, x squared minus 1. 4x, x plus 1, x minus 1. Not only do I have one location, which is guaranteed by the mean value theorem, I have 3. Great. However, I failed to do something which is very, very important. And that is, the requirement for a function to use the mean value theorem. To use the mean value theorem, my function must be differentiable. And it's like tricky to think about, like, how can I show that a function is differentiable? How can I show that there's no sharp points anywhere? Well, when we talked about continuous, and if I looked at the continuity of this function, you'd say there's no denominator, we're continuous. And you'd be correct. If I want to show differentiability, that means we have a tangent slope for this anywhere on my interval. Well, that means if our derivative is continuous, that means there is a tangent slope that exists for all of these points on this function. That means we are differentiable. So to show a function is differentiable, you're going to look at the continuity of its derivative. So since f prime is continuous, f is differentiable. After stating that, we can then use the mean value theorem. Okay. Same thing. First, understand we want tangent slopes equaling secant slopes. We'll find our 2 points to find our secant slope. I go down 3 over the course of going over 3. So my secant slope is -1. When does my tangent slope, which is continuous, that means f is differentiable, give me a secant slope of that, I get -1/2. It's pretty cool. You can kind of visually see that quickly. If you have x squared between -2, 4 and 1, 1, there's my secant slope. My tangent slope would be like right there. That tangent slope's -1/2. Sine, same deal. Understanding mean value theorem equates tangent slopes and secant slopes. Sometimes we forget, or we haven't talked yet about why. Why is the mean value theorem important? With the intermediate value theorem, we were able to show that certain solutions to equations exist. Like if I gave you, I don't know, some wild equation, and I said, show me that this function equals pi somewhere. And it's something that you couldn't solve. Well, all you needed to do is find a point below and above pi and say, yeah, I know I have a solution. Where it is, that's the question. I don't know, but I know that there is one. This is the same thing for slopes. The mean value theorem is a way to show that we are guaranteed to have certain slopes. Certain tangent slopes. Okay, it actually ends up being used pretty frequently in proofs for other calculus things we'll be talking about in the future. Here, I get a secant slope of 0, cosine x equals 0, when does cosine equal 0, pi over 2, 3 pi over 2, et cetera, et cetera. Okay, great. The question was like, determine whether mean value theorem can be applied. Well, again, look at your derivative. So it's continuous, means f is differentiable. So yes, it can be applied. Check. Find all values of c to show its application. Well, mean value theorem guarantees a value in your interval. This value in your interval. Great. Mean value theorem guarantees a value in your interval. This would be the only value that we would say the mean value theorem guaranteed. The 3 pi over 2, that's just an extra value. It just so happens outside your interval you also had this location. Mean value theorem says there's at least one location inside your interval. So I'd only actually be concerned with this pi over 2. Let's look at this. Let's look at the slope of the secants. We got f of 4, 4 minus 1, which is 3. F of 1, 4 minus 4, which is 0. So I've gone up 3 units over the course of 3 x units. So average rate of change of 1. Tangent slope. Make sure we know this is negative 4x to the negative first. Derivative of 4 is 0. Derivative of minus 4x to the minus first would be positive 4x to the negative second. This equals 1. Ooh, okay, I got a problem here. Or do I? Let's see. F prime is equal to 4 over x squared. This is not continuous everywhere. So, since it's not continuous, f of x is not differentiable at x equals 0. Turns out it's definitely not differentiable because we don't have a function value at 0. We have a vertical asymptote at x equals 0. So, man, does that mean I shouldn't be using the mean value theorem? The answer is no, because on your interval from 1 to 4, even though f prime is not continuous at 0, it is continuous from 1 to 4. Since it's continuous on your interval, we are good to use the mean value theorem. So f is differentiable on the interval. We can use the mean value theorem. Let's do it. I get 4 is equal to x squared. X equals plus or minus 2. However, the mean value theorem only guarantees that this 2 exists. So there you go. We know it must exist. We found the location. And that 2, not the negative 2, because it's in my interval. Now, same thing. Turns out, like with our intervals, as long as it's differentiable on our open interval, we're fine. Because what we'd find with this one is that we are not continuous. F prime is not continuous at 0. But that's okay, because between 0 and 1 we are. So that means f is differentiable from 0 to 1, because f prime is continuous on that interval. We need to find our secant slope. F of 1 is 1. F of 0 is 0. So the slope is 1. 1 minus 0 over 1 minus 0. Solve this. Flip both sides. Maybe cross multiply. Whatever you want to do. 2/3 is equal to x to the 1/3. Cube both sides. 8/27 is equal to x. 8/27 is inside my interval. Okay. There's a couple extra problems about using a calculator. I'm not going to worry about that. We are not going to use our calculator. I thought we might, when I first started creating these notes, we might utilize our calculator a little bit, but nope, we're going to stay calculator free for the remainder of this unit and moving forward. Okay, I hope we understood the mean value theorem and finding possible locations of maxes and mins for functions.